Before we get into the actual properties of bone and what determines the mechanical strength, there are three formulas here that are important to know. The first one is volume fraction. Volume fraction is defined as the volume of, in this case, bone tissue inside a sample of a bone. So as we explained previously, the bone, a bone cylinder, let's say a femur, a long bone, it's not 100% bone. It has a marrow in it, and the porous spongy bone has a lot of space within it, a lot of fluids and the likes. So how would you calculate the actual amount of bone inside the bone, if that makes sense, to see the actual strength of it? What we would do is take the volume of the bone tissue. In other words, it's like if we had a bone and then powdered it up and just seen the volume of just the tissue itself, and then divide that by the bulk volume, the volume of the entire bone as it is. So if you would assume the bone was a cylinder, then the bulk volume would just be the volume of the cylinder, whereas the volume of the bone tissue would be just the volume of just the bone in that cylinder. You would remove everything out and just measure the volume of the bone. But how would we calculate it, let's say, in a lab? We're going to use these two other formulas. The apparent density is the mass of the bone tissue divided by the bulk volume. So you're going to measure how much that bone tissue weighs and then divide it by the volume of the whole thing. And the tissue density would be the mass of the whole bone divided by the volume of the bone. In other words, that is the same thing as bulk volume. If we divide the apparent density by the tissue density, as you can see over here, we're going to have the volume of the bone tissue divided by the bulk volume. And you can notice here that research has found out that after 20 years, this apparent density will decrease 2% per decade. In other words, the mass of actual bone tissue, of calcium phosphate or collagen fibers that give the bone the strength and durability, would diminish 2% every decade, even though the volume of the bone may not change. Okay, now looking at the mathematical relationship we have over here, the ultimate stress, which is basically the amount of stress that a material can withstand before it just completely fractures, the ultimate stress, and comparing that to apparent density, we can see there's some form of exponential relationship. In other words, when the apparent density increases, we see that the strength of the bone gets substantially stronger, and that's important. And we can see over here, this is the typical graph, very typical graph of a bone sample. We can see that there is a linear portion over here, and then it goes steep out to some plastic region over here. But I don't know if you can see it. There's actually two lines coming on here. The first line is an old bone sample, and the second one is actually a young bone. And we can see that even though the properties at a lesser strain will be very similar to an old and young bone, we can see that after a certain amount of strain, the old bone will fracture, whereas a young bone can be able to withstand even much more than an old bone. So we can see here, this is young bone. Okay. Now some more mathematical formula. We can see over here, assume this is a bone sample, cylindrical. If we apply a bending moment, so this is called a three-point bending, we apply a force here and then two opposite forces over here, we can see that what's going to happen is there is going to be an internal moment. How do you calculate the moment at this point? The bending moment is equal to the moment produced by these two, the moment produced at that point, times, my bad. The bending stress is equal to the moment produced at this point times the distance, if this is a cylinder, the circumference of this point, sorry, no, the radius of this point, that's what I meant, the radius, and then divided by, as you see here, I. And I, my bad, 1 second. Yeah, sorry. I is the inertia. We call the inertia. And that's basically used when we try to find moments around three-dimensional objects that are not quite the simple form of torque thing that we learned. Force times distance would be a torque. It'll be a little more complicated than that. Because the moment produced at this point would be a different, separate formula than just force times distance. Okay, so we have the inertia over here. For a sphere, we can see here, if this was a cross-sectional area of this shape, then the inertia I would be the radius. If we assume this is radius r, it would be pi r to the 4 over 4. That is what I is. If we assume that there is a hole inside the bone, in other words, it's like a hollow cylinder, then the formula would just be pi, the radius of the bigger radius to the 4th minus the smaller radius to the 4th, divided by 4, and you're going to have the moment of inertia. If we apply torsion, so twisting moments, opposite direction, this one twists this way and this one twists that way, the twisting, there'll be some kind of twisting force, and it usually will crack at an angle something like this. This is where the crack will occur. And to find the stress produced by torsion, it will simply be the moment times the radius times the moment of inertia, and again, that's the same value over here, depending if it's a filled cylinder or like a hollow cylinder, and the likes.